A light climbs the inner sky, then vanishes. The calendar says late October, the physics say peak heat, and the geometry pulls a curtain across our view. For 4 weeks, the most watchable thing becomes unwatchable while it passes its closest approach. Instruments idle, data streams thin to nothing. If something unusual were to happen, this is when it would happen, inside the glare. Listen closely, stay with me through the noise and the quiet, because when the light returns, we will know whether the story changed. Every great space story begins with a constraint. In this one, the constraint is not fuel or distance, it is the sun itself. The visitor we are following moves into a slice of sky where our telescopes cannot safely point, and where scattering light from the solar disk drowns delicate signals that would otherwise be routine. The clock ticks toward perihelion, the point of closest approach to the sun for this object, and the same clock ticks toward a communications winter for observers on Earth. Control rooms that usually hum with overnight tracking plans begin to erase slots from the schedule. The oddest feeling settles in, the feeling that the most active phase will unfold in a room with the lights off. This blackout has a name, and it is completely natural. Solar conjunction is the alignment that places the sun between Earth and a target, turning a bright star into a wall of glare. The wall does not care about our curiosity. It does not care that this object has already proven itself interstellar by speed and shape of orbit. It only cares about geometry. During conjunction, sensitive observatories follow strict keep-out rules. Ground-based mirrors avoid the hazard zone. Space telescopes respect thermal and pointing limits. Even instruments that specialize in the sun are built for coronal arcs and flares, not for a faint body that stays well outside their narrow fields. The result is silence, not forever, only long enough to raise the stakes. Silence can be useful. In the quiet, you learn what you are waiting for. We know exactly which measurements will matter the moment the object slides away from the sun's halo. We will want position checks against the predicted path to see whether gravity alone explains the journey. We will want brightness trends to see whether heating followed natural curves or jumped in ways that suggest structure or fragmentation. We will want spectra to see whether the strange dominance of one volatile over another persisted or began to normalize under fresh sunlight. The first days after reappearance can answer months of speculation, which is why the days before disappearance feel charged. There is another reason the blackout feels uncanny. It arrives wrapped around a coincidence that is simple to state. The weeks when sunlight cooks a small body most strongly are often the weeks when the sun blocks our view from Earth. The physics of sublimation and the geometry of alignment share the same stage. That overlap is not a plot twist, it is a consequence of orbits. Yet when a story already contains rare ingredients, even ordinary overlaps can sound like whispers. People begin to ask whether a window of invisibility during maximum change is only a curiosity, or whether it is an opportunity for events we would miss in real time. It remains uncertain whether such questions lead to answers or to mirages. What matters is that the questions can be tested after the curtain lifts. Think of the coming month as an intermission with homework. Teams schedule the last looks they can steal at high elongation. Amateurs note star fields where reacquisition will be easiest in twilight. Software overlays the predicted ephemeris on sensor task lists so that the first clear nights after conjunction are already spoken for. We do not stand still when we are blind. We prepare the eyes that will open later. None of this implies danger to Earth. The closest approach to our planet is comfortably distant by any public metric, and the global agencies that track impact risks have been direct about that fact. What is at risk here is not safety, it is certainty. The loss of continuous observation threatens to import ambiguity into later arguments. If a small deviation appears after the gap, advocates of natural jetting will point to unseen activity near perihelion. Advocates of control will point to the same gap and say the timing is interesting. The only antidote is a plan to measure early, measure often, and compare the numbers to predictions that were written down before the light went away. So we begin with a paradox that is both ordinary and electric. The sun powers the show and hides the stage. A rare visitor peaks in activity while the audience is asked to close its eyes. The solution is patience mixed with preparation. When the object returns to dark sky, the test begins for all the claims you will hear. We will be ready to score them, not by volume, but by fit to reality. Stand over a model of the solar system and picture a thin, luminous disk where the planets circle. That disk is the ecliptic, the highway where most of the heavy traffic lives. Interstellar visitors usually cut across that plane at bold angles. They rush in like stones through a window, then they are gone again. This one slides almost along the lane. Its inclination sits near 175 degrees, which means it moves in the opposite sense to the planets, yet it does so only about 5 degrees above the flat. It is retrograde, but it hugs the sheet. The picture that forms is not of a reckless intruder, it is of a body that glides with a strange courtesy, like a boat taking the marked channel. Numbers make this less poetic and more concrete. An inclination near 175 degrees places the orbit nearly mirror flat relative to the planetary plane. The angle from the ecliptic is small. That detail would be unsurprising for a long-period comet from our own cloud. For an interstellar object, it is enough to raise a brow. Most things that enter from the deep galactic reservoir have orientations that ignore the habits of our system. They arrive from directions that reflect the chaos of ejection from unknown stars. Here we have a countercurrent traveler that still respects the line where our planets sail. What does that mean? One possibility is that selection effects help pick our mysteries. We scan the skies most efficiently near the ecliptic because our surveys tend to live there. A visitor that moves along the plane is simply more likely to cut through the regions we patrol with the sharpest cadence. A competing view suggests that ejection processes in other systems may prefer disk planes, so their castoffs depart in sheets, and some of those sheets will align with ours by chance. It remains uncertain whether either effect dominates. The important point is that neither interpretation requires intention, yet the mind keeps noticing the choreography. This path grazes Mars on a date we can write on a calendar. It runs to perihelion when our view will be lost. It moves on toward a measurable pass by Jupiter, as if ticking boxes. Evidence is limited, but one inference is that a low inclination makes those intersections with major bodies more probable during a single inbound sweep. The corridor is crowded, targets are plentiful. The idea that this feels like a plan is an emotional echo of that geometry rather than a proof that someone set it. There is also the small matter of retrograde motion. Moving backward through a ring of forward-moving worlds increases relative velocities. The slipstream grows harsher. If you were piloting something fragile, you might avoid this choice. If you were designed for it, you might not care. A minority view holds that a retrograde track along the ecliptic could reduce the time spent at high solar latitudes, where fewer assets watch, while still sampling the places where plasma and dust and magnetic fields get interesting. Another simple view holds that this is where dynamical dice happen to roll. The two views can coexist until data dislodges one. Think about how we test this. We ask whether the plane-hugging path is matched by other oddities, or whether it stands alone as an elegant accident. If the path were the only surprise, then the default would be a natural origin with lucky alignment. If other anomalies collect around it, chemistry and light behavior and timing quirks, then the case file grows heavier. We avoid grand statements. We keep asking for independent lines that point the same way. Visualize the lane again. Planets move in patient circles. Our visitor crosses those circles almost edge-on. The tilt is slight, the backward sense pronounced. From certain longitudes, the motion looks like a thin silver wire laid across a dark plate. Observers love such lines because they are efficient for scheduling. You know where to look. You can hand off from one site to the next. The same trait that eases logistics also feeds suspicion. Easy things feel engineered. Nature does not care about our shift calendars. The last piece to hold is humility about samples. We have only a few confirmed interstellar arrivals in the modern record. One came in at a steep angle and behaved oddly. Another looked like a normal comet in chemistry and form. This one is flat in its geometry and complex in its story so far. 3 cases cannot anchor a distribution. They can only remind us that variety is real. The lane-hugging path might be rare, or it might become unremarkable once we have dozens more examples. The only cure for that ignorance is time under sky, so we file the shape of the track in our memory. Almost flat, retrograde, 5 degrees off the plane, a corridor that happens to pass interesting places at interesting times. We accept that coincidence can produce this pattern. Then we ask the next question. If the path is unusual, do the surfaces and gases tell a similar tale? The answer lives in light that carries the chemistry of the coma, and that is where we turn next. There is a simple figure that decides where a traveler belongs, a curve that says family or foreigner. Draw a circle for a bound orbit, stretch it to an ellipse for a long wanderer, push it farther, and the curve snaps to a parabola. Go beyond that limit, and the line opens into a hyperbola, a path that never closes. That is the signature of escape, and it is the language this object speaks. Its eccentricity is well above 1, not a rounding error near the threshold, and that single number declares origin and destiny. It did not start here, and it will not stay. Speed is the second signature. You can feel it in the way the trajectory threads the inner regions. A hyperbolic excess remains after solar gravity has taken its due, a leftover velocity that refuses capture. Observatories hand the target from longitude to longitude because the window at each site is short. The track moves briskly against the stars, and ephemeris updates matter because small timing slips can mean a missed night. When you fit all the measurements, the solution is clear. This is not a member of the long-period cloud that loops back over millennia. This is a passerby from the interstellar sea. It helps to translate that into physical intuition. Imagine rolling a marble toward a heavy bowl. If the marble's energy is low, it falls in and circles. If the energy is just right, it crests the rim and glides along the edge, barely balanced. If the energy is greater, it crosses the bowl, climbs the rim, and keeps going. The sun is the bowl. Our visitor crosses and climbs and does not look back. The number that encodes that behavior is the eccentricity. Anything greater than 1 is a traveler on a one-time visit. The measured value here sits far beyond that threshold. The conclusion is not subtle. Multiple teams saw this. One survey first flagged the motion, then others confirmed and refined. That relay is how confidence grows, because instruments have quirks, and nights have weather, and reductions have traps. When sites with different optics and different pipelines recover the same path and the same excess, doubt shrinks. The community does not need drama to agree on a basic identity. The orbit is unbound. That part is settled. What an interstellar label does not tell us is who this traveler is on the surface. There are no guarantees about activity level or chemistry, simply because the origin is elsewhere. We have already seen that lesson once. One interstellar arrival was quiet in dust yet showed odd acceleration. Another looked like a textbook comet, rich in familiar volatiles and classic in appearance. This third case writes a new line in the ledger by combining a nearly flat geometry with a hyperbolic speed, then layering on a suite of optical and chemical curiosities that complicate any neat category. Hyperbolic motion also reframes risk and opportunity. There is no capture in our future, no leisurely series of apparitions to build a long archive. The inbound pass is the field season, and the outbound leg is the farewell. That imposes urgency on every choice we make. It also protects us from certain anxieties, because a path with this energy and these distances cannot suddenly turn into a threat to the planet. The agencies that monitor hazards watch the same numbers and make the same conclusion. The danger here is not impact. The danger is that we squander a rare chance to learn. The identity of the curve can seem like an abstract point, but it anchors every discussion that follows. If the orbit were closed, then unusual chemistry could be chalked up to a local history inside our own reservoir. If the orbit were marginal, then tiny non-gravitational effects might push it one way or another and make classification murky. Instead, we have a clean message. The traveler came from outside the sun's family, and the sun will not keep it. That clarity narrows the live hypotheses when we interpret the rest of the data. It is easier to picture a formation environment in a distant system than to force this case into a familiar box. There is still humility in the fit. Astrometric solutions tolerate small noise, and cometary bodies can release gas in uneven ways that nudge their course. That is why the post-blackout reacquisition will matter so much. If residuals appear after the gap, they will be measured against a baseline that is already pinned down by an interstellar solution. Any deviation will be seen in contrast to a curve that was clean and unbound before the quiet. That contrast will help sort natural jets from something more deliberate, if anything more deliberate is truly there. One sentence to keep us aligned: we are building a test of nature against intention by securing the basics first, and the hyperbola is the first lock that holds the rest of the argument in place. Put a ribbon of dates across the inner solar system and mark 3 points. The first sits in early October near Mars. The second sits in late October near the Sun at perihelion. The third sits in mid-March near Jupiter. The object does not pause at these waypoints, but the geometry at each position offers a distinct vantage, a different set of instruments, and a different set of physical forces. A calendar becomes a sensor. Time becomes baseline. The sequence is simple to read and rich to interpret, which is why it frames the rest of the investigation. Begin at Mars. Around October 3rd, the visitor passes at a distance that is not a close skim, but close enough for orbiters to try. Cameras that usually stare at dust storms and polar caps can turn and look outward for a faint moving envelope. Spectrometers that read thin gases above the red planet can collect a whisper of light from the coma. The angle from Mars to the Sun to the object is not the same as the angle from Earth. That difference can make a jet face toward one observer, but not the other. It can reveal asymmetry that a single viewpoint would miss. Even if the data are grainy and hard to calibrate, a few frames from a shifted seat can narrow debates later. If a forward brightening is real rather than an illusion, a second perspective can help prove it. Slide the ribbon forward a few weeks. Perihelion arrives in late October at a distance inside the orbit of Earth. Heating rises, outgassing should peak, tails lengthen, and coma structure can change as ices release. At the same time, the Sun fills the field for any telescope near Earth. We have described the blackout, but it is worth repeating why the timing matters here. The chemistry could reorder during this period. If water lagged at larger distances, but begins to dominate as deeper layers lift, then a ratio seen earlier as unusual may begin to drift toward more ordinary values. If iron lines have been shy while nickel lines stood out, then iron may appear as temperatures rise. In a natural picture, this evolution is expected. There is no need to invent a new process to merge. We will not see the change as it happens, but the aftermath should carry a signature of what transpired in the heat. Advance the ribbon to March 16th and draw a circle around Jupiter. The pass is not within the realm of capture. It is still tens of millions of miles away. That does not make it dull. Jupiter is a lighthouse of magnetism and plasma. Dust grains pick up charge in that environment. Ion tails can kink and wave in electric fields. If an object has conductive structure, even at small scales, it can interact with that environment in ways that differ from a diffuse rubble pile. Long baseline observation matters here as well. Stations on Earth can watch. Spacecraft in the Jovian system can watch if their geometry allows. The angle differences allow a reconstruction in 3 dimensions of coma and tail features. If nothing unusual is present, the maps will still be beautiful and useful. If something winks or flickers in a regular pattern, or if the tail responds in a way that theory did not predict, the files will grow thick with new work. The order of these events produces a narrative that is hard to resist. A first glance from a neighboring world, a long quiet during peak change, a final exam in a strong magnetic field. The order also tempts the mind into thinking that purpose is written into the dates. One possibility is that we feel this pull because the human brain likes tidy arcs. A competing view suggests that a low-inclination path naturally threads multiple planets in short succession, so the schedule looks careful even when it is unplanned. It remains uncertain whether that second view fully explains the neatness of this chain. The answer belongs to statistics that we do not yet have, because 3 interstellar visitors do not define the normal. This calendar also tells us how to prepare. Before Mars, planners request slews and test exposure settings so that a dim coma is not lost in a bright background. Before perihelion, teams freeze predictions into a set of numbers to test later, so there is no temptation to move goalposts. Before Jupiter, modelers push plasma codes and scattering codes so that expected shapes are clear. After each date passes, reality can be compared to those plans. If the Mars view shows nothing new, that result is still a constraint. If the post-perihelion composition shifts toward water, that becomes a point for the natural scenario. If the Jovian pass is serene, that is another point. If any step surprises in a way that stands up to repeat checks, then the anomaly score increases, but only by the amount the data earn. By laying the encounters on a simple belt of time and distance, we gain a common language. Viewers can follow without specialized math. Observers can slot their work into a shared frame. The object will not adjust its travel for our convenience. We adjust our curiosity to the places where nature allows a look. Next, we turn from when and where to what, and ask what these eyes have already seen in the light from the visitor's sunlit face. Stand in a dome at noon and try to pick out a firefly that hovers near the sunday. You cannot. The dome is the sky, and the firefly is a cometary coma, and the reason is simple. Glare floods every sensor we have. Solar conjunction is not a mystery. It is a limit that comes from optics, safety, and geometry. The sun is so bright that diffused light spills through the atmosphere and through telescope structures, then blooms across detectors. Even in space, the problem persists. Space telescopes are built with strict rules that keep their optics and instruments out of hot zones. When a target slips close to the sun from our perspective, those rules force a pause. The pause is temporary. It is enough to hide the busiest act. On the ground, mirror coatings and baffles are not magic. They control stray light when the source is far from the field, not when the source sits nearby like a white furnace. Observatories also protect themselves. Pointing near the sun can damage domes, sensors, and cooling systems. Schedulers carve out keep-out angles as if they were fences. Once the object moves into that fenced region, nights that were useful become red on the plan. You can stare a little to the side and try to catch a tail in the wing of the field, but the contrast collapses and noise masquerades as signal. Teams do not accept that risk unless the payoff is overwhelming, and for this target during this window, it is not. In space, physics tightens the noose. Telescopes that live near the Earth follow pointing rules that protect thermal shields and optics from sunlight. If an instrument warms, calibrations shift, and sometimes hardware is harmed, the safest choice is to wait. There are solar observatories with coronagraphs that block the disk to study the corona. Their fields are tuned to comets that skim very close to the limb. Our visitor stays too far from that narrow frame to be caught cleanly, and its brightness is modest. You cannot force a tool to do a job it was not built to do. You work with the geometry you have. What about clever workarounds? Radio occultation can sometimes reveal a large body when its presence perturbs radio paths from spacecraft that sit beyond it. That requires alignment at radio wavelengths and a sizable object. Our traveler is small. Gravitational lensing is fantasy here. There is no mass to bend starlight in any measurable way. Thermal infrared watching from other spacecraft could see a hot rocket plume if one existed, but absent a large burst, there is nothing for those eyes to see. The blackout is not absolute across the solar system, but for civilian instruments that publish quickly, it comes very close. Why does the timing sting? Because perihelion falls inside this quiet. As the object approaches the sun, heat rises and volatiles sublimate. Natural comets often brighten, show new jets, and sometimes shed pieces. If this one follows that script, the key changes might start near the end of October. We will not watch the moment-by-moment evolution. We will read the aftermath. That is still powerful. Chemistry leaves traces in spectra. Orbits remember integrated nudges. Morphology carries history. A split nucleus is obvious. A changed tail texture is observable. A new ratio of gases can be measured. But the continuous film will be missing, which means arguments will spring up about what happened while we stared at glare. The good news is that you can plan a return to site with method. Before the gap, observers lock down predicted positions and predicted brightness so that any later difference has a clear baseline. During the gap, mission teams near Mars try opportunistic glances because their angles differ from ours. After the gap, the first nights focus on astrometry and quick spectra, not on beautiful pictures. Beauty can wait. Numbers must come first. If the object appears where gravity says it should, if the light follows a smooth curve, if the spectra show evolution that matches heating, then a natural interpretation gains strength. If the object arrives late by more than noise, if the brightness jumps in a way that theory does not expect, if the spectra refuse to drift toward water as temperatures rise, then the anomaly score creeps higher. Another reassuring truth holds through the quiet. Impact risk does not grow with our ignorance. The geometry that keeps us from looking also keeps us safe. Closest approach to Earth remains far. The lack of live video does not change trajectories that were already measured. What hangs in the balance is not safety but understanding. We will either tell a clean story about natural processes under stress, or we will tell a more complicated story that asks for new mechanisms and tests them against evidence. The mechanics of the blackout give us one more lesson. Limitations focus the mind. Knowing what you cannot see sharpens your plan for what you will see later. We will carry that discipline into the next turn, where light itself behaves oddly, bright on the face that meets the sun, as if something more than dust is at work. Look at a classic comet, and you see a soft lantern. The nucleus hides inside a mist of dust and gas. Sunlight scatters, and the brightest region wraps the core in a near-symmetric haze. This visitor does not quite play by that rule. In several datasets, the sunward face looks oddly assertive. A plume lifts toward the light rather than away from it. The antisolar tail is present and faint. The forward side gleams with a firmness that makes observers pause. Is this only a trick of geometry, or is something on the sunlit surface doing more than passively reflecting the day? Begin with what is not controversial. Multiple images show activity consistent with a healthy coma. Dust grains ride gas that escapes the warmed surface. Pressure from sunlight sweeps that material back, which is why tails point away from the star. When you inspect the images carefully, however, the pattern is not perfectly even. Brightness piles up near the subsolar region. The transition across the face looks steeper than a textbook envelope. Photometric cuts through the core do not relax into a gentle bell. They show a shoulder near the light. This is where debate starts, and it starts for good reasons. One possibility is that the nucleus hosts jets that concentrate toward the side that faces the sunday. Many comets do this. Active pits or fractures can favor certain directions because of rotation and topography. If the spin state places a vent near the day side for a long stretch, the coma will swell asymmetrically. A competing view suggests that we are seeing an optical effect that grows from viewing angle and dust size. Large grains scatter light forward more efficiently than small grains. If such grains dominate during this epoch, a bright lobe can appear sunward even if the gas is isotropic. It remains uncertain whether jet geometry or scattering physics, or both, explain the glow. Better phase coverage will help sort the options. There is a more adventurous interpretation that some thinkers entertain as a thought experiment. Evidence is limited, but one inference is that the sunward brightness could indicate active thermal management on a surface that controls heat rather than only enduring it. In such a story, material vents preferentially toward the sun to carry away energy, much as a radiator would. The plume would then be less of a passive fountain and more of a designed exhale. This is a minority view, and it lives or dies by future tests, not by evocative language. To lift it above speculation would require correlated signs such as a light curve that shows locked orientation, or a spectral line that pulses with a mechanical cadence. At present, we do not have that level of structure. Natural processes offer rich explanations that deserve first seat. As the object warms, crusts of sintered dust can crack and expose volatile pockets. Bursts of gas carry fresh grains that are larger and darker than the older haze. Forward scattering strengthens, the sunlit arc pops, and the camera records what looks like a headlight. Later, as smaller grains refill the coma, and the rotation brings a different facet to the day side, the lobe fades. This behavior has been seen in other active bodies. The open question is whether the amplitude of the sunward brightening here sits within the envelope of normal cases or pushes past it. Polarimetry and time are our allies. Polarization patterns map grain sizes and shapes. If the forward glow comes from large compact grains, the angle dependence of polarization should announce their presence. If it comes from directed jets, the pattern should rotate with the body and reveal a geometry that tracks the spin. High-cadence imaging can also catch transient fans that rise and fall in minutes rather than hours. Those fans have a signature that models can reproduce. If the glow is steady through phase angles where forward scattering should weaken, that steadiness would be notable and worth independent confirmation. The conversation needs one more guardrail. Cameras that push near the limits of contrast and resolution can fool us. Deconvolution can build artifacts that imitate structure. Background stars can stitch phantom lines across a moving target. Teams who reported the bright sunward shoulder have been careful about these traps, yet replication matters. Different telescopes, different filters, and different pipelines should recover the same asymmetry. If they do, then the glow is real and merits center stage. If they do not, then we have learned a lesson about the danger of elegant pictures that whisper more than they know. Where does this leave the story? The forward glow is either a normal cometary feature exaggerated by geometry and grain population, or it is a clue to a process that is less common. It does not yet require a leap beyond nature. It does require better phase coverage and higher signal observations. Those will come after the blackout. When they do, the glow will either relax into the family of known behaviors, or it will stiffen into an outlier that feeds the next steps in our test. A brief reorientation, we are weighing natural structure against intention by following the light and its chemistry with predictions that can be checked when the object returns to dark sky. When spectra first came back, The lines at 4.3 micrometers rose like a choir. Carbon dioxide sang far louder than water. The ratio was not a gentle tilt, it was a steep stack, about 8 parts carbon dioxide for every 1 part water in the recorded epochs. For most comets, water is the main act. It vaporizes as sunlight warms the nucleus, and it drags dust into a glowing skirt. Here, dry ice seems to call the tune. Maps from infrared instruments traced a carbon dioxide envelope that reached hundreds of thousands of kilometers from the core, nearly a lunar distance in scale, a cold balloon hanging in the dark. There are natural stories that fit this odd chemistry. One possibility is formation beyond a carbon dioxide snowline in a system colder than ours. In that environment, dry ice would be common. Water ice would still exist, yet the outer layers might lock in far more carbon dioxide than we see in typical cloud comets here. Another explanation leans on processing in interstellar space. Cosmic rays and ultraviolet light can change the top few centimeters of a surface over long times. That work can seal water under a crust that resists early release. Carbon dioxide, with its lower sublimation temperature, sneaks out first and floods the coma while water waits for deeper heat. A competing view suggests that water ice can be trapped in grains in forms that release slowly, so the early act is dominated by volatiles that escape with less help. All three accounts are friendly to physics, and none require invention, yet the scale is still startling. An envelope of carbon dioxide that large means the gas is not only present, it is abundant and active over a wide region. It remains uncertain whether we are seeing a transient phase that will mellow as temperatures rise, or a stable signature of composition that will persist through perihelion. Evidence is limited, but one inference is clear. The evolution of this ratio across the next month will carry heavy weight. If water ramps up as the object warms, and the ratio drops toward parity, the natural crust and grain stories gain strength. If the dominance of carbon dioxide holds even as solar input peaks, then models will strain and seek new structure. There is also a practical engineering thought that some raise as a controlled speculation. Carbon dioxide can serve as a working fluid for heat management. It sublimates at low temperature and can carry energy away in a clean exhale. If a surface were built to keep temperatures in range near a star, venting carbon dioxide sunward would be a simple strategy. A minority view holds that such a system could mimic what we see, a broad carbon dioxide coma with little water and a forward-leaning plume. That vision demands tests that go beyond imagination. We would look for stability in the ratio when thermodynamics say it should vary. We would look for periodicity that reflects control rather than geology. We would look for line features that correlate with a cadence. Even without any engineered story, the chemistry gives us a powerful set of predictions. As the nucleus rotates, patches with different volatile mixes will turn through sunlight. If carbon dioxide is carried by a few dominant vents, the coma should wobble in composition on the timescale of the spin. If the mix is global, the ratio should hold steady through a rotation and change only as the mean temperature rises. Polarimetric signals can help. 2. Since carbon dioxide outflow often carries larger grains that polarize light differently than water-driven haze. In short, the gas and the dust should tell the same tale if we listen closely. We must also guard against the lure of single-epoch excitement. Instruments see through apertures that clip different parts of the coma. Some integrate over large regions where weak water lines are easy to drown. Others stare tight at the inner few thousand kilometers where fresh release hides. Calibration and background subtraction can push weak features below detection. That is why sequences matter more than snapshots. A run of spectra through changing geometry will beat one perfect night, and independent teams with different hardware will beat one pipeline. For viewers who do not swim in wavelengths and line ratios, there is one simple frame that holds the meaning. Most comets taste like water, with a hint of carbon dioxide. This one tastes like dry ice with a faint trace of water. If that taste changes as it cooks, nature smiles and closes the question. If that taste does not change when heat rises, we return to the table with new theories. Either way, the numbers will settle the argument once the object steps out from the sun again. We will measure, we will compare to the predictions written in ink, and the ratio will tell us whether the lantern in the dark is ordinary in an unusual way, or unusual in a way that asks for a deeper story. When spectrographs traced the coma in visible and near ultraviolet light, a curious signature rose from the noise. Nickel lines stood tall and clean, while iron lines that usually march beside them stayed faint or late. In planetary materials, these two metals are partners. They condense together in stellar forges. They travel together in meteorites and cores. Seeing one speak while the other whispers makes chemists lean forward in their chairs. What could lift nickel into view while keeping iron in the wings? Is the answer in the dust, in the gas, or in the way light teases atoms into glow? Begin with the familiar. In ordinary comets, metal emission lines often trace grains that vaporize close to the warm face. As the object approaches the sun, microscopic flecks of metal or metal-bearing minerals heat, detach atoms, and those atoms radiate at characteristic wavelengths. Iron is usually part of that chorus. Here, the chorus sounds different. Nickel sings solo, or at least sings louder. The simplest natural thought points to chemistry that frees nickel more easily than iron, at the temperatures and photon flux in play. One possibility is the presence of organometallic carriers that hold nickel in bonds that break under modest heating or ultraviolet light. Such compounds can travel in dust and release nickel atoms at larger distances than raw grains would allow. A competing view suggests that iron may be present but hidden, trapped in less volatile phases or grains that do not release atoms until the heat rises further near perihelion. If so, iron lines could be late bloomers rather than missing actors. It remains uncertain whether either path alone can explain the observed contrast. There is also the question of measurement geometry. Spectrographs have slits and fibers that sample specific regions of the coma. If nickel-rich gas is more extended than iron-rich gas, an instrument that sums over a wide aperture can overweight the nickel. Evidence is limited, but one inference is that different spatial scales for release could produce an apparent skew that later resolves when instruments aim closer to the nucleus. This is why a campaign that stacks inner coma measurements against outer coma measurements matters. Profiles that map line strength against distance from the core can turn hand-waving into a physical picture. Another idea sits at the intersection of thermal physics and microstructure. Nickel-bearing grains may have sizes and coatings that absorb sunlight more efficiently than iron, bearing grains at the wavelengths present. A small change in absorption can lift temperatures by tens of degrees. That lift can push nickel features above detection thresholds, while iron remains quiet. As the object heats further, the iron threshold is crossed and its lines appear. This account needs time series data to stand. If iron lines strengthen as perihelion passes, then the delayed threshold story gains a point. If they do not, curiosity deepens. Then there is the speculative fork that many would like to close with data. A minority view holds that non-thermal processes could sort metals in ways that mimic intent. Directed heating, electric fields within structured dust, or even engineered release from smooth surfaces could bias nickel over iron. If anyone entertains a surface that controls its own temperature, nickel might emerge in effluence because of specific chemistry in that process stream. Such talk is a thought experiment, not a claim. It asks for signatures beyond a simple line ratio. For example, correlated periodicity in nickel features tied to a rotation that remains stable through changing phase, or a polarization state that suggests smooth facets rather than rough-grain clouds. Without such structure, chemistry remains the first language to try. There are practical tests within reach once the glare ends. High-resolution spectra can search for iron at levels just below earlier limits. If iron rises on a slope that tracks the temperature curve, the natural map holds. If iron stays anemic while nickel refuses to fade, the map wrinkles. Laboratory work can also help by measuring likely carriers of nickel and iron under vacuum and light to constrain which pathways produce the observed lines at plausible distances from the sunday. Polarimetric imaging can add a layer by estimating grain sizes that accompany the nickel-bright epochs. If large compact grains are present, forward scattering and specific polarization angles should announce them. We should also be honest about how easy it is to chase a ratio into a story. Data reduction for faint metal lines is a demanding craft. Sky emission lines and instrumental features can masquerade as weak signals or hide them outright. Independent teams with different instruments must reproduce the nickel lines and the iron limits at similar epochs before we let narrative momentum carry us. That caution has already begun to pay off in past cases, where apparent anomalies softened when a second spectrograph weighed in. For a general audience, the meaning can be kept simple without losing truth. In rocks and meteors, nickel and iron are like siblings. They appear together. In this coma, they do not. If the quiet sibling speaks up as the object warms, The family bond is restored and we learn something about timing. If the quiet sibling stays quiet while the other keeps talking, then we have met a household that challenges our expectations. That is when the anomaly score moves, not because we wish it, but because the numbers insist. Curiosity loves scales. When a storm approaches, we look at categories. When a quake hits, we look at magnitudes. With strange visitors, we need a ruler that measures how unusual they are and how close a case comes to technology. A simple spectrum runs from commonplace to engineered. At the low end are objects that behave like the crowd. At the high end sit objects that show signatures we would expect from tools, signals that repeat, shapes that hold angles, light that modulates with intent. Most things land near the floor, a few climb. Where does this traveler fall right now, and what kind of evidence would move it? Begin with the ground rules. High scores require markers that cannot be waved away as dust or chance. A narrow band radio tone that repeats at fixed intervals across multiple receivers that would vault a case up the scale. A light curve that shows a non-natural cadence. A beat that tracks a stable orientation through changing. Phase that would move the needle a long way. A resolved image that shows planar facets, or geometry that is hard to carve from ice and rock by simple stress, that would be decisive. We do not have such markers. What we do have is a bundle of oddities that sit in the middle of the spectrum where debate lives. Now, set the present position. Geometry that hugs the ecliptic and runs retrograde. Chemistry that favors carbon dioxide over water by an unusual margin. Metal lines that give nickel a head start over iron. A forward glow that may be scattering, or maybe jets that aim near the subsolar point. None of these alone forces a leap. Together they raise eyebrows. The honest placement today is a high middle score. Interesting, not decisive. The strength of this placement is that it can slide. New data can lower it with ease. A single clear natural mechanism that explains the chemistry and the glow would push the case toward ordinary. New data can also raise it if the behavior after the blackout refuses the simple scripts. A scale is useful only if it guides action, so we set 5 levers that can move the score. The first lever is astrometry. Positions should match gravity, once heating and known jet forces are accounted for. If residuals appear that cannot be fit by standard outgassing models, the score rises. The second lever is spectroscopy. If the carbon dioxide to water ratio evolves as expected with temperature, the score falls. If it locks in despite strong changes in heating, the score rises. The third lever is the metal pair. If iron lines emerge and track nickel as perihelion passes, the score falls. If nickel stays lonely, the score rises. The fourth lever is the light curve. Natural rotation plus jet modulation should produce patterns that models can match. If a stable external cadence appears that does not fit, the score rises. The fifth lever is polarization and morphology. Natural dust should yield angles and textures that obey known phase laws. Failure there would matter. We must also set thresholds that restrain excitement. One team reporting a surprise is not enough. Multiple teams with independent pipelines must see the same thing. One night is not enough. Features must persist across epochs that sweep through different geometries. One instrument is not enough. A pattern that appears in visible light should agree with the infrared story where possible. When those conditions are met, the scale earns trust. When they are not met, the score stays where it is. What about the human urge to force a verdict? It helps to think in probabilities rather than slogans. Most comets are normal under the hood, even when their surfaces look dramatic. A minority carry unusual ratios or odd dust. A smaller minority defy quick explanation and sit on our shelves for years. We set priors that reflect this landscape. Then we let the 5 levers move the dial. If all 5 fall toward natural, the case drifts down. If 2 rise while the others fall, the case stalls in the middle. If 3 or more rise with solid replication, the case climbs. There is a reason to keep this score in public view. Viewers can watch without becoming experts. An easy chart can show the 5 levers week by week. A green arrow lowers, a red arrow raises. A grey bar waits for data. That display turns a noisy debate into a shared process. It also teaches a discipline. Claims move the score only when they cross the replication line. Hot takes do not count. Strange pictures without context do not count. Numbers that repeat across tools count. Now return to the blackout. The scale will sit in its current band while the object is hidden. The instant the light returns, the levers can move fast. Within days, the positions will lock, the spectra will start to tell a story, the light curve will sketch a rhythm. That is why patience is not mere waiting. It is time spent setting the frame so that quick data can snap into place. One sentence to hold our path. We judge the unknown by rules we set in daylight so that surprises in the dark cannot trick us into believing what we only want to see. When the glow returns from behind the sun, the first hours will matter more than the weeks of talk that came before. The plan is simple to say and careful to execute. We will measure 5 families of signals that together can separate a strange natural world from something that implies control. Each family is familiar to working observers. None requires magic. All of them gain meaning when compared against predictions that were spoken aloud before the blackout. The first signal is position as a function of time. Astrometry is the habit of turning photons into coordinates with patience and calibration. Observers fit star fields and remove distortions. A point of light gives a centroid that can be tied to a frame. With several nights in hand, an orbit refit can be run that compares the real sky to the path predicted by gravity. Natural comets drift a little because jets act like tiny engines on rough surfaces. Those drifts can be modelled once spin and activity are known. If the residuals after such modelling remain stubborn and coherent, if they point in a direction that refuses the physics of casual outgassing, the case for control inches up. If the positions fall into line once the usual comet terms are added, the case for nature strengthens. The second signal is chemistry through spectra. The carbon dioxide to water ratio that looked so lopsided before perihelion should evolve as temperature climbs and falls. Water is often late to the party because it needs deeper warmth. Carbon dioxide arrives early. If the object behaves like a processed yet natural world, the ratio should loosen and drift toward parity, then perhaps invert. Lines for other species should rise and fall in families that match thermodynamic expectations. If instead, the ratio locks into place through a wide temperature swing, or if a specific molecule persists at the level that ignores heating and cooling, then we must look for structure that goes beyond geology. Repetition across instruments and sites is the rule here. A line that appears once is not a law. The third signal is the metal pair. Nickel has already spoken. Iron has been quiet. As the object approaches and passes perihelion, iron lines should emerge if delayed thresholds are the culprit. Their strength should grow along a slope that maps to rising heat and closer dust grains. If iron refuses to appear while nickel keeps its voice, then the family bond has been broken in an odd way. A natural fix would require carriers and grains that treat the two metals with unusual selectivity across a wide range of conditions. That is not impossible. It asks for evidence beyond a single evening. High-resolution work that separates faint iron lines from sky features will be the arbiter. If iron arrives, the tension relaxes. If not, the question persists. The fourth signal is the light curve. Every rotating body modulates its brightness as surfaces turn through sunlight. Comets add another layer because jets turn on and off as vents face day and night. Natural curves can look ragged yet still obey models once the spin period and the geometry are fit. A suspicious curve would show regularity that does not depend on phase angle in the way dust should. It might repeat with a clock that stays steady as the object moves through different scattering angles. It might show sudden steps that repeat in a way that hints at deliberate timing. Any claim of an engineered beat must survive checks with different apertures and different wavelengths. Scattered light can mimic rhythm. Only wide replication defeats that trick. The fifth signal is polarization and morphology. Polarized light reveals grain sizes and shapes because scattered electric fields remember how they met the particle. Natural dust has patterns across angle that decades of studies can predict. If the coma polarizes in ways that break those patterns, or if the structure of the tail shows edges and planes that are hard to make from random debris, the conversation changes. High-cadence polarization can also test the sunward glow. If that bright face is ruled by large, compact grains, the polarization fraction should advertise them. If it is ruled by directed jets, the pattern should turn with the body. These 5 signals are not independent in the messy world of real data. A change in composition can drive a change in light curve. A shift in dust can alter both polarization and astrometry through jet forces. That is why teams compare notes in near real time. The strength of the method is not in any single check. It is in the way the 5 lines of evidence can converge on a story that holds together without strain. If they converge on ordinary, that is a victory for understanding. If they converge on odd, that is a victory for honest curiosity. One more promise before we step forward. We will move the anomaly score only when at least two of these families point in the same direction with replication. That rule protects us from elegant noise. It also gives any surprise the weight it deserves. The path through the next month will be easier to walk with these 5 signals in your pocket. When the object returns to dark sky, you will know exactly what to watch and why it matters. Rarity attracts story. When a path lies almost flat along the planetary plane, when a blackout swallows the most heated weeks, when encounters line up with Mars and Jupiter in the same season, the mind wants intention. The safer habit is to ask what the numbers would say if we had enough of them. With only a handful of interstellar visitors on record, probability becomes a room with thin furniture. We can sit for a moment, but we should not lean too hard. Still, there are ways to think clearly about coincidence that keep awe and caution side by side. Picture a sphere wrapped around the Sunday. Interstellar arrivals could come from any direction on that sphere. The ecliptic is a narrow belt on that surface. Landing within a small angle of that belt is not impossible. It is simply less common than landing at a random tilt. If survey telescopes dwell near the belt, then our catch will favor it. That is selection. We look where we like to look, so we tend to find what lives there. A plane-hugging visitor is therefore natural to spot, even if similar bodies cross at high latitudes in silence. This does not empty the oddity of meaning. It places the oddity in a context where our own habits share the blame. Now consider the blackout. Perihelion is the time when heating climbs. Solar conjunction is the time when our view collapses. For objects near one astronomical unit, these two facts can overlap often. There is no cosmic rule that forces perfect alignment. Yet orbits arrange many cases where the hot spell and the blind spell share a month. When that happens inside a story already loaded with strangeness, the overlap reads like theatre. It feels scripted. A calm voice reminds us that physics has no taste for drama. The sun simply sits where it sits, and we sit where we sit, and geometry runs the lights. Time on a calendar can also seduce us. Mars on an early October date, a peak near the end of the month. A Jupiter pass on a tidy day in March. Waypoints become chapters, chapters become a tour. One possibility is that a low-inclination path raises the odds of crossing several planetary longitudes within a season. Planets occupy a ring, and a flat path meets the ring often. A competing view suggests that the sequence is not only frequent, but also useful if anyone wished to watch many worlds in short order. It remains uncertain which view will win once a larger census exists. With 3 interstellar objects in hand, there is no base rate to lean on. How do we keep from sliding into story-shaped traps? We write predictions that do not flex with mood. If the geometry is coincidence, then the after-blackout measurements should follow the thermodynamic script. Water should rise as deeper layers warm. Iron should join nickel as temperatures pass thresholds. The orbit should need only known jet forces to fit. If 3 or more of these checks land in the natural bin, then the chain of alignments is a curiosity rather than a code. If several checks refuse the natural bin, then the same chain begins to look like more than luck. A second guardrail is to separate eye-catching alignments from energy budgets. People will ask whether a retrograde plane hugging path tells us about control. Control costs fuel or its equivalent. An engineered plan would leave fingerprints that are not just pretty geometry. It would leave accelerations that resist the models. It would leave rhythms that hold through changing phase. Without those, a line on a chart remains a line, not a plan. Geometry can suggest where to look. Geometry cannot prove agency without help. There is comfort in humble arithmetic. On a sphere, the fraction of sky inside a small band is small but not tiny. On a calendar, conjunction windows eat weeks, but not months upon months. On a map, Mars and Jupiter sit where they sit, and a fast traveller can come within useful distance of both inside half a year. None of these pieces alone deserves capital letter wonder. Together they can still make an honest heart race. Wonder is not the enemy of reason, it is the fuel that keeps eyes on the sky while data arrives to tame it. So we hold 2 ideas at once. Coincidences can stack without intent. True plans would use the same stack. Only measurement can tell them apart. The cure for thin furniture is more chairs. Time will bring more interstellar cases, and the belt of the ecliptic will either fill with flat arrivals or it will stay spare. Until then, We resist verdicts that lean on mood. We let the next measurements write the next page. Imagine a ship that is not a ship, a husk that crosses interstellar space with patience, then opens its hand near a star. The hand does not have to be literal. It could be a field of small bodies that separate, each with a task, each too faint to notice in a single casual look. This is the carrier idea, a thought experiment that asks a simple question. If a visitor were more than a single chunk of ice and dust, what would its behavior look like from far away? The answer lives in tiny signatures that are hard to fake with ordinary comet physics, and in a discipline that keeps fantasy on a leash. Begin by listing signals that are plausible yet unusual. One possibility is a series of micro-brightening events that last minutes, not hours, as small pieces detach or surfaces are exposed. Such spikes would ride on top of the normal rotation pattern like quick breaths. They would repeat without a stable period, since releases would depend on mission choices rather than spin. A competing view suggests that natural venting can produce bursts of similar shape when a crust fails. It remains uncertain whether cadence alone can sort the two. That is why cadence must be paired with geometry. If spikes occur when the sunward face is steady through changing phase angles, the case strengthens. If spikes follow expected jet modulation, the case weakens. A second possible signal is a specular radar glint. Natural nuclei are rough. Their echoes spread softly. A smooth facet can act like a mirror for radio, sending a sharp reflection when the orientation is right. Evidence is limited, but one inference is that a brief, strong echo at a predictable rotation angle would be hard to attribute to a pile of rubble. The practical barrier is distance. Only a few facilities can transmit and receive at the needed power, and time is scarce. If a window opens after the blackout, even a null result will constrain how smooth any surface could be. A third line of evidence might be a faint train of companions that trails the main body after the blackout. Fragmenting. Comets do this, so the signature is not unique. The difference would be in order and spacing. A break from heat and stress produces shards of many sizes on chaotic paths. A planned release could produce a set of points with similar brightness and gentle separations that grow with a steady rate. A minority view holds that even a planned release would be jostled by gas and solar pressure into patterns that resemble debris. That is a fair caution. High-cadence astrometry of any companions would need to show consistent relative motion over days to rise above the natural case. There is also the thought of radio or optical modulation that arrives only during the blackout, then vanishes. This is the most dramatic version, and it is the least likely to be shared in real time given who holds which instruments. A better approach is to set modest tests in public hands. If periodicities appear in post-blackout data that were predicted before the gap, those patterns gain weight. If not, the idea retreats to the shelf. The power of a thought experiment is not in the image it paints, but in the falsifiers it proposes. So, we write them down. If the light curve after reappearance shows only rotation and jet patterns that fit known models, the carrier idea loses oxygen. If spectra evolve as heating predicts, and no narrow lines repeat with a mechanical cadence, the idea loses oxygen. If astrometry requires only standard outgassing forces, the idea loses oxygen. If radar sees only a fuzzy echo, the idea loses oxygen. 4 strikes are not required. 2 or 3 solid hits are enough to return the carrier to the drawer, marked interesting but unnecessary. We also write down what would raise the idea without breaking our own rules. A stable, repeating modulation that matches a period unrelated to rotation and unrelated to viewing angle would be one. A radar flash that recurs at a stubborn orientation would be another. A coherent set of faint followers that keep tidy spacing over many days would be a third. None of these alone would prove design. Together they would demand deeper study with sterner tools. There is a human reason to keep this experiment alive for one more part. Minds are good at filling blanks. Give them a blackout and a mystery and they will sketch faces in the fog. The next step is to build guardrails against that impulse, not to kill wonder, but to keep it honest. We turn now to the methods that protect us from seeing what we want in noise, and to the habit of writing predictions before the data return. Before the data return, the human brain has already drawn conclusions. It sketches lines between bright pixels. It hears rhythm in uneven noise. This is not a flaw. It is an ancient feature that helped our species survive. In astronomy, it can also mislead. The craft is to keep our pattern engine engaged while bracketing it with rules. We build procedures that slow the leap from image to intention. We write our expectations in ink before the first post-blackout plot appears. We commit to tests that would make us abandon favorite ideas. That is how curiosity stays honest. Begin with pre-registration. Teams can publish short notes that list specific predictions and specific thresholds. They can say how much the orbit may drift if natural jets are the cause. They can state what carbon dioxide to water ratio they expect to see if deeper ice begins to release. They can set a minimum strength for ion lines that should appear within a few days of perihelion if delayed heating is real. They can define what kind of phase curve structure would count as an anomaly rather than a fit to rotation. These thresholds must be measurable with the instruments at hand. They must be tied to the times when data will arrive. Once written, they become a shield against post hoc storytelling. Replication is the next pillar. One team can be fooled by weather, by pipeline choices, or by a subtle instrument quirk. Two teams using independent hardware and methods can still be fooled if they share hidden assumptions. Three teams working blind to each other's intermediate results rarely share the same ghost. The rule we can live by is simple. No claim moves the anomaly score until an independent group sees the same feature at a similar epoch and geometry. This does not slow discovery. It makes discovery more believable and more durable. It also calms the public square, where first reports often arrive without context. Blinding helps when judgment is soft. A light curve analyst can fit periods against a shuffled time label and only unlock the true timeline after the model is fixed. A spectroscopist can define the algorithm for line detection on simulated data, then run it untouched on the real frames. An orbit fitter can set acceptable residual ranges from the pre-blackout arc, then apply the same ranges to the new points without tuning. These habits are common in other sciences. They work here because they separate desire from procedure. The cosmos does not care about our hopes, and our code should not either. Language is a tool. We can temper our verbs and still thrill. It remains uncertain, invites attention without pretending knowledge. Evidence is limited, but one inference nudges an audience toward the contingent nature of early work. A competing view suggests honors debate rather than dismisses it. We can also set a scale of confidence for every claim that appears on screen. A simple three-color legend can do the job. Green for replicated and consistent, yellow for emerging and needs confirmation, red for speculative and fun yet unproven. Viewers learn the code within minutes. The code then protects both trust and wonder. Open data accelerates correction. Calibrated images, spectra, and astrometry tables can be posted with the plots that use them. Scripts that produce the figures can be shared with version tags. This does not mean dumping raw telemetry without context. It means providing enough material for a skilled peer to reproduce the claim. When mistakes happen, and they will, the fix arrives in days rather than months. The lesson echoes through the audience. Science is self-repairing when the parts are on the table. Social media is both amplifier and fog. A gorgeous image with a bright sunward lobe will race around the world in minutes. Without scale bars and phase angles, it can seed myths. We can pre-format shareable frames that carry the missing context. A small caption can note the elongation, the filter, and the predicted cause of the feature in plain words. We can also pin a short thread that lists the 5 signals, the current status of each, and links to living dashboards. Information wants to be vivid and correct. We can give it both. There is a final humility to hold. Sometimes, the best story is the most ordinary. A coma that looks like headlights may relax into symmetry with better phase coverage. A chemical ratio that seems wild may drift toward normal as temperatures rise. A nickel solo may turn into a nickel and iron duet as thresholds are crossed. Guardrails prepare us to accept that outcome with grace. They also prepare us to accept the opposite if it arrives, because strong methods make strong surprises believable. We step from method back to narrative with one more question. If someone wanted to do something while our eyes were turned by the sun, would they? Humans have used geometry as cover since the first missions left Earth. The next part looks at that playbook, and at why even good cover leaves tracks for patient observers to find. Space is a stage with bright lights and blind corners. The brightest light is the Sunday. The blind corner is the region around it where our instruments go quiet. If anyone wanted to act unseen, this would be the tempting place. The idea feels cinematic, almost too neat. Yet it has a sober precedent in our own history. Mission planners have wrestled with solar geometry since the first probes left Earth. They have used quiet windows to reduce risk, to save hardware, and sometimes to move without the world watching every second. Geometry is a tool. It is also a trap for the unwary, because physics writes a ledger that auditors can read later. Start with the Moon. During each Apollo pass behind the lunar far side, contact dropped to 0. The capsule vanished behind a grey horizon. Engineers in Houston stared at plots and waited for the voice to return. Critical burns happened inside that silence. The famous trans-Earth injection on a far-side pass meant that confirmation came only when the ship reappeared and the radio link snapped back to life. No one called it secrecy. It was simply a consequence of stone between antennas. Still, the shape of the event shows a rule that holds everywhere. In the moment, silence. After the moment, evidence. Move to Mars. Every 26 months, Earth, Sun, and Mars line up. During that period, radio waves struggle through the solar wind and the corona. Commands risk corruption, telemetry degrades. Agencies put Mars spacecraft into safe or quiet modes. Rovers stop driving. Orbiters record data and cache it. Teams plan low-risk activities and wait. It is a ritual now. The pause is expected, and it pays off in hardware survival. It also means that if a small change happened to a spacecraft or a target in that window, the record would contain a gap. Operations resume later. Analysts reconstruct what likely occurred by comparing before and after states. Now picture that same logic applied to a visitor near the Sunday. The object slips into a region where Earth-based observers step back. Even several space observatories cannot point there. The urge to imagine a hidden maneuver is natural. It may even be healthy if it spurs better measurements afterward. The question is not whether a maneuver could be hidden from real-time public view. A modest one could. The question is whether it could be hidden from physics. The answer is no. Change, velocity, and the path changes. The new path carries the memory of the impulse. When sightlines open again, patient astrometry will see the offset if it is larger than the noise that jetting can explain. Thermal signatures deserve a brief look as well. Large hot burns announce themselves across the solar system to sensitive infrared eyes. Smaller cold gas puffs do not. If anything deliberate happened during the blackout, and it was gentle, there might be no public thermal clue. Yet even the gentlest push will weave into the orbit. That is the ledger. Orbits are unforgiving accountants. They do not accept cash payments in myth or mood. They accept only numbers. There is also a social parallel to consider. Defense satellites and classified sensors exist. They watch for rockets and for glints and for heat. Their data are not broadcast. That does not mean public science is helpless. We build our case from what can be shared. We frame our questions so that later, if a surprise appears in an official paper, we have a place to fit it. The tradition in planetary science is that dramatic claims require open data in the end. Instruments that claim a discovery must eventually show their work. The same tradition will govern any anomaly attached to this visitor. A press rumor cannot move the anomaly score. Only evidence can do that. Consider the motivations that sometimes get projected onto a silent maneuver. People ask why an object would choose to change course when no one can see it. One possibility is simply convenience. If the natural activity near perihelion is strongest, then any small controlled change would be camouflaged inside that dust and gas. A competing view suggests there is no reason at all, because the course is ballistic and jet physics explains it. It remains uncertain whether any change will appear at all. Predictions are ready to meet the data either way. The lesson from our own playbook is clear. Solar geometry can reduce scrutiny for a while. It cannot, to erase footprints. When contact returns, the first task is to compare the path to the pre-written ephemeris. If the match is clean, the drama fades and the audit closes with a natural verdict. If the match is off and the offset resists models of outgassing, the audit stays open. That fork is not a source of fear, it is a source of focus. We know what to test. We know what would count. We step from the idea of action inside the glare to a more grounded beat. Before the curtain falls all the way, Mars has a side view. That vantage may be limited, but even a thin angle can show a feature that Earth cannot. The next part looks at that brief window and what it might add to the ledger. Imagine the scene from another shore. While Earth begins to turn its face away, spacecraft above Mars pivot their cameras and spectrometers to take a sideways glance. The geometry is modest but meaningful. The line from the Sun to the visitor to Mars is not the same as the line to Earth. A jet that hides from us may tilt into view from the red planet. A faint arc that dissolves in our glare might stand out against dark Martian night. No one promises crisp portraits. What these orbiters can give is a change in perspective, and in a story that hangs on geometry, even a small offset is a gift. Mars Express has been circling the planet for years. Its instruments recognize thin gases and shifting ice at the poles. With careful commanding, some can be turned outwards to taste the light of a passing coma. A spectrometer tuned for planetary air can still catch the broad bands of common volatiles if the target is bright enough. The trace gas orbiter is another set of eyes. Built to sniff the faint breath of methane above Mars, it holds spectrometers that can read sunlight that has scattered through dust and gas beyond the planet. If the signal is weak, teams can co-add frames, stacking minutes into hours until ghostly lines emerge. The exercise is delicate. The instruments were not designed for roaming comets. That is why the expectations are sober. A few clean detections would count as success. What could these side glances reveal? First, a check on the sunward brightening that puzzles earthbound observers. If the forward glow is a trick of phase, then a different phase should soften it. If the forward glow persists at the new angle, that constancy would argue for structure on the day side rather than a simple scattering effect. Second, a sense of the carbon dioxide envelope at a time, near but not yet inside the blackout. Instruments that favor the infrared could map the reach of the dry ice plume in a way that complements Earth-based measurements. Third, any early stirrings in the metal lines could be caught, though this is the longest shot. The bandwidth and sensitivity for such fine features may not be there. There are limits that we must admit plainly. Spacecraft at Mars are busy. They watch dust storms and image canyons and relay data from surface explorers. Pointing at a moving interstellar target must fit around these duties. The visitor's path across the Martian sky is fast. Tracking it will challenge guidance systems that were tuned for steady landscapes. Even if a window opens, the signal to noise will be lean. A null result will not disprove a feature. It will simply fail to confirm it. That is why these attempts are framed as opportunistic. They can sharpen questions. They cannot close a case alone. There is still value in the choreography. If Mars sees a jet that aims slightly off the line we expected, orbit modelers can fold that direction into predictions for post-blackout drift. If Mars sees a temporary brightening on the sunward limb, photometrists can search for the same signature when Earth regains the view. If Mars sees nothing at all, that quiet can be used as a bound. The forward glow would be capped. The envelope would be measured low. Bounds are science as surely as detections. Think of the pipeline that would make this work. Commands are written, tested, and timed. Instrument teams rehearse background subtraction that will be tricky because Mars itself glows in infrared and reflects sunlight in broad bands. Downlinks arrive with other traffic. Analysts extract a handful of frames and lay them beside the latest Earth-based spectra. The combination may look like two pieces that do not quite fit. But small overlaps can be enough. A notch here, a faint shoulder there. Piece by piece, a picture forms that is better than either view alone. One possibility is that these views from Mars find only normal behavior, a soft coma, a faint tail, and little else. That is still a useful story, because it tells us the strangeness is not visible from every angle. A competing view suggests that a directional plume will betray itself from at least one off-axis vantage, and that Mars is well placed to catch that betrayal briefly. It remains uncertain whether the cadence and sensitivity will be enough to decide the matter. The attempt will be made because cost is low and potential payoff is high. The handoff from Mars is not to victory or defeat. It is to the bright wall ahead. Perihelion waits inside the glare. Heating will peak as our instruments on Earth turn away. What Mars may glimpse will soon be swallowed by the Sunday. The audience must sit through that quiet, then spring to work as soon as the curtain lifts. The purpose of this part is simple. A small side door might open before the main door closes. A one-sentence reorientation, we are following a chain of vantage points that begins with Mars, falls silent at the Sun, and resumes with a hard audit of what changed while we could not see. Picture a kiln with a stone at its heart. The door closes, heat climbs. You cannot see the surface, yet the chemistry and the stress evolve all the same. That is perihelion inside the quiet. The visitor turns its sunward face toward an unforgiving lamp. Temperatures rise across crust and clefts, volatiles hidden beneath dust wake and try to escape. In any normal comet, this is the act that fills the stage with light. In this case, the stage lights are in our eyes. The sun from Earth looks like a floodlight that erases contrast. The object moves through its hottest days while our instruments blink and wait. The sense of suspense is not a trick. It is the shape of the geometry. Start with the physics that does not care about our schedule. As the subsolar point sweeps across the nucleus, energy flows inward by conduction and outward by sublimation. Thin crusts that form during long cold years may crack. Cavities can vent. Dust layers can slough and expose fresher ices. Water that was quiet farther out can begin to steam. Carbon dioxide can surge from pockets that connect at last. The coma responds like weather. Jets form. Fans broaden. The anti-solar tail lengthens and bends in the solar wind. None of this needs agency. It is the dance of heat and escape in a gravity field too weak to hold much. Perihelion is the natural peak of this dance. Now lay that process against the checklist we wrote before the blackout. If the earlier chemistry was dominated by carbon dioxide, then the simplest expectation is a swing toward water as heating deepens. If iron was late to speak while nickel led, then those iron lines should rise as thresholds are crossed. If forward brightening came from large grains that favor the day side, then the lobe should wax and wane with phase and might soften as finer dust joins the coma. These are not poetic hopes. They are standard consequences of heating a mixed surface. When observations resume, every feature that fits this script will lower the anomaly score a notch. It is fair to ask what else could happen in the heat. One possibility is fragmentation. Thermal stress can split a nucleus if voids run deep and strength is low. Such events leave clear signatures. The light curve jumps. The coma texture turns clumpy. The tail shows knots that drift apart at gentle speeds. A competing view suggests that even a split can mimic a planned release if the fragments align by chance along the track. It remains uncertain whether the internal structure of this visitor encourages a clean fracture or merely sheds small pieces. If a split occurs during the quiet, we will find only the afterimage. That will be enough. Positions of fragments can be measured. Their relative motion can be traced backward. A natural break has known kinematics that will either fit or not fit. Another possibility is a subtle non-gravitational push that integrates over days. Jets that aim persistently off-center can deliver a small change in velocity. A few centimeters per second spread over weeks can shift the path by thousands of kilometers. Such a push is exactly what outgassing can do. It is also exactly what control could do. The separation comes from pattern. Natural jets tend to track spin and illumination. Their effect can be modeled once shape and rotation are known. A push that fails those fits and remains coherent in a fixed inertial direction would be odd. The first astrometry after reappearance will be the test. We will not know when a change occurred. We will know that it did. Perihelion is also when dust-size distributions can flip. Coarser grains can be lofted at last. Finer grains can be eroded. Polarization is sensitive to this shift. If the forward glow was partly a trick of large grains that favor forward scattering, then the polarization fraction near the sunward limb should change as the mix changes. A steady polarization state through a large temperature swing would be notable, not because it proves design, because it resists the most common explanations. Notable features deserve replication. They also deserve restraint in language until that replication lands. During the quiet, work does not stop. Models run with bracketing assumptions. Teams generate families of possible orbits that include a range of jet parameters. Spectroscopists draw temperature curves and predict the day when water should overtake carbon dioxide in strength. Photometrists simulate light curves for plausible rotation periods and jet maps so that a match or a mismatch can be declared quickly. The aim is to reduce the time from first post-blackout photons to first judgments about which script the world followed. Preparation is not bias. Preparation is a defense against the rush to conclusion that follows any long silence. The scene inside the glare, therefore, has two layers. In the physical layer, ice meets light and change follows. In the human layer, expectation meets measurement and judgment follows. The danger is not that the visitor will do something dramatic. The danger is that we will tell the wrong story, because a gap in the middle invites fantasy. The cure is to hold the predictions in hand and to grade them coldly. When the object comes back into the dark, The first numbers will feel like a breath after a held lung. We will try not to gasp. We will try to count. The first frame after the blackout will not be pretty. It will be a grainy rectangle of sky where stars have been subtracted and small residuals twitch along the rows. Somewhere inside that field, a point that does not belong will sit a little off from where the pre-written ephemeris predicted. Or it will sit exactly there. Either way, the room will tense as the centroid routine locks and the coordinate appears on screen. This is the moment when numbers begin to replace guesswork. The visitor steps out of the glare. We begin the audit. Reacquisition is a choreography that has been rehearsed. Wide fields sweep the predicted corridor first to make sure the object has not wandered beyond the tight windows. Difference imaging subtracts a fresh frame from a template so that moving points pop like sparks. Once a candidate is found, the mount tightens its field and exposure times adjust so that trailing does not smear the target. 2 or 3 more. Frames confirm motion along the predicted track. The night does not pause for beauty shots. Astrometry comes first. Positions go to the pipeline. A new fit is run against the pre-blackout solution. The initial residuals appear. A hush makes room for them. If the residuals lie inside the envelope that jet models expected, that will feel like a soft landing. The crowd of explanations for earlier oddities will thin. If the residuals are coherent and larger than expected, that will feel like a gauntlet thrown. Orbit fitters will add non-gravitational terms and spin state assumptions to see if an ordinary comet can still explain the drift. If those terms fail, and the fit still refuses to settle, then the anomaly score will tick upward, not because of poetry, but because gravity plus known jet physics cannot hold the path. That outcome is rare. It is not impossible. Teams will be ready for either result. Chemistry follows close behind the positions. Early spectra will not be deep. They will be quick looks, designed to answer 2 questions. Is water rising? Is iron speaking? If the ratio that made headlines before the gap begins to slide toward parity, the narrative of a processed natural surface gains strength. If iron lines that were shy now rise with the heat, the nickel solo becomes a duet, and the exotic explanations retreat. If the carbon dioxide to water ratio holds stubbornly near its earlier value while the temperature curve says it should not, then unease returns. If iron still refuses while nickel stays tall, the file grows heavier. Single nights will not settle this. A sequence across days will. That sequence will be planned already, with exposure times and wavelength settings written into scripts that observers can run by habit. Light matters in a third way. Photometry with high cadence begins as soon as the pointing stabilizes. The goal is a clean light curve across hours and then nights, with consistent apertures and careful background estimates. Rotation. Signals should emerge if the nucleus and the coma behave like their cousins. Jet modulation should bring small asymmetries that models can fit. Suspicion would grow if a steady cadence sits on top of the curve that refuses to shift with changing phase angles. That would be a drumbeat that does not belong to dust. Claims like that will be held to a high bar. Multiple instruments, multiple passbands, multiple longitudes. Repetition is the only antidote to wishful thinking. Morphology and polarization will lag by a day as deeper integrations are scheduled. The first images will still show shape. Is the sunward face as assertive as before? Does the tail texture look smooth or knotted? Are there hints of fragments near the core that would argue for a split during the quiet? Polarization maps, even if coarse, will begin to pin grain sizes that can validate or challenge the forward glow story. If large compact grains still dominate where smaller grains should have joined by now, that will be noted. If the polarization fraction rotates in step with event, that will anchor a jet model at last. Communication will be as important as collection. Teams will publish quick look reports that are honest about uncertainty. A simple table will show the 5 signals with green or yellow or red markers. Green for consistent with natural expectations, yellow for ambiguous or evolving, red for out of family. Viewers will see the same chart that analysts use. Claims will be labeled with confidence rather than wrapped in adjectives. The goal is not to dampen excitement. The goal is to keep trust intact while wonder does its work. There will be noise. Clouds will steal plan nights. Instruments will throw calibration fits after long stretches off target. Pipelines will need small fixes that must be documented to avoid any hint of tuning to a preferred result. That is why several teams will chase the same measurements in parallel. Redundancy is not waste. It is resilience when the First nights after a gap carry more weight than usual. If there is a single sentence that carries the mood, it is this. The first light after the gap is not a verdict. It is the opening argument that will either confirm a natural script or demand a deeper cross-examination of the strange. Brightness is not only about how much sunlight falls on a surface, it is also about angles, grains, and rhythm. The phase curve is our map for that world. It plots brightness against the angle between the sun, the object, and the observer. For dusty comet, there is a known family of shapes. Forward scattering near small phase angles lifts the curve. Backscattering gives a different shoulder. Embedded in that smooth shape is another kind of story, the heartbeat of rotation and of jets that turn on as vents see daylight. If we can separate the smooth phase law from the pulse of rotation, we can tell whether the light behaves like weather or like machinery. The first task is to build the curve cleanly. Observers will span a range of phase angles as the object moves along its path after the blackout. They will keep apertures consistent, calibrations steady, and reference stars stable across nights. With that discipline, a baseline emerges. Natural comets usually track this baseline in a way that models can fit with a small number of physical assumptions. Dust size distributions, grain porosity, and the balance between gas and dust production are enough to explain the arc. Deviations do occur. They tend to be localized near times when new vents open or when fragments break away. Those deviations look like bumps or dips that pass and then give the stage back to the baseline. Now add the heartbeat. Rotation imprints a recurrence in the light. The amplitude depends on shape and on albedo, and contrasts on the surface. The period depends on the spin state. Jetting adds its own beats as vents enter sunlight and then fall into night. A healthy coma can blur these features, yet the patterns remain. Astronomers can recover them by folding the light curve on candidate periods and by fitting harmonics that account for lumpy geometry. The point is not to prove elegance. The point is to show that a single physical model fits many nights without the need to retune as the phase angle changes. Suspicion would rise if a clock appears that does not care about phase or about rotation. Picture a gentle sinusoid that keeps the same period and phase through a swing in viewing geometry that should alter how light scatters from dust. If the peak always arrives at the same absolute time each night, regardless of angle, if the troughs line up in a way that resists the expected modulation, then we ask harder questions. One possibility is that an unseen binary or a complex tumbling shape can emulate such stability. A competing view suggests that a persistent external cadence is more likely to arise from an active surface that controls emission with timing rather than with sunlight. It remains uncertain whether any cadence of that kind is present. The burden of proof would be severe. Multiple longitudes must see it. Multiple passbands must agree. Any claim must survive injections of synthetic signals designed to fool the pipeline. There is also the matter of color. If the light curve heartbeat is driven by dust, the amplitude will vary with wavelength according to grain properties. A larger amplitude in the red than in the blue, or the reverse, can put numbers on the particle sizes at work. If the amplitude is nearly achromatic, that can mean geometry dominates over dust. Achromatic stability across a wide span would be interesting. Once again, interesting does not mean artificial. It means we reach for models that do not lean on simple one-vent pictures. Perhaps a large flat facet rotates into view in a way that repeats faithfully. Perhaps a ridge controls how jets shadow each other. The data will tell us which paths are worth walking. Polarimetry strengthens this test. The degree and angle of polarization are also functions of phase and grain properties. If polarization swings match the light curve pulses, then dust physics carries the day. If polarization refuses to follow, while the brightness beats on a steady drum, then a more exotic mechanism would gain attention. Radio and infrared monitoring can add another layer by catching thermal inertia or plasma interactions that modulate with time. Cross-discipline agreement is how confidence grows. Noise and temptation complicate this work. Clouds, seeing, and scattered moonlight can fabricate short-period wiggles. Aperture choices can bake in fake periodicities if stars drift through the photometric ring. Analysts will blind themselves to the real-time sequence by shuffling time tags during algorithm design. They will only reveal the true order after the method is fixed. That is how we deny our brains the chance to pull patterns from static. If the phase curve settles into a familiar arc, and the heartbeat resolves into rotation and jets that models can fit, then our story of a natural comet under heat grows stronger. If the curve refuses to fit, and a stubborn clock survives every attempt to explain it with dust and shape, then the anomaly score moves a notch. Neither outcome is a disappointment. Both are answers to a question that only patient light can resolve. Jupiter waits like a storm lantern on the far edge of the calendar. The visitor will not dive into its moons, it will not thread the rings of dust around the giant, yet the pass is close enough for the planet's environment to matter. Jupiter is not only a world, it is a magnetic weather machine. Its field balloons outward and drags plasma with it. Charged particles race along lines that curve into auroras big enough to swallow Earth. When a dusty, outgassing object wanders near that domain, even at tens of millions of miles, subtle interactions can leave fingerprints for those who know where to look. The gauntlet is not to a test of courage. It is a chance to see how the traveler conducts, charges, and sheds under electrical stress. Consider first the tail. Neutral dust follows sunlight and solar wind pressure, sometimes making gentle curves that we can model with particle sizes and radiation pressure. Ionized gas behaves differently. It couples to magnetic fields and can kink and ripple as it meets new domains. As the visitor approaches Jupiter's reach, any ion tail may pivot or form knots that drift along the field lines. Those shapes can reveal the charged state of the coma, the mass loading of ions into the local plasma, and the presence of conductive paths through dust clumps. If nothing special happens, the tail will glide on, shaped mainly by the Sunday. If it twists in a way that matches Jupiter's rotating field, then plasma physics will have a feast. Now think about timing. The planet's magnetosphere rotates with Jupiter's short day. That rotation drags magnetic perturbations past any object nearby. If the coma carries charged grains, brightness variations can sync to that rotation as particles focus and disperse along field lines. Astronomers on Earth can time those modulations against radio emissions from Jupiter that mark its spin. A phase lock between the two would not imply control. It would imply coupling. That coupling would tell us how easily the grains charge and how quickly the coma responds to field changes. The rhythm would be a natural metronome, a probing wave that scans the visitor without our help. Jupiter also provides geometry. Observers on Earth and in orbit around the planet see the same object from very different angles. That long baseline is a gift. If multiple teams capture the coma and tail within the same hour, analysts can reconstruct the three-dimensional structure of features that usually flatten into two-dimensional pictures. A lumpy arc seen from one vantage becomes a ribbon in space when seen from two. With that reconstruction in hand, models can test whether jets are narrow or broad, whether dust sizes differ along different directions, and whether any odd planar structures exist that would be hard to carve from rubble. A flat facet would cast reflections predictably across the baseline. A cloud would not. There is a harder question that will hover over this pass. Could a conductive structure reveal itself by interacting with the magnetic field in a way that diffused dust cannot? One possibility is a sharp change in polarization as a flat, possibly smooth region rotates through an angle where field-aligned currents could run. A competing view suggests that any such effect would be swamped by the coma's chaos at this distance. It remains uncertain whether our instruments have the sensitivity to separate such fine signals from the background. The prudent approach is to plan observations that could see a strong effect and to accept that a null result will be the most probable outcome. A null result still helps by setting bounds on how smooth or large any facet could be. Radio and plasma wave instruments aboard spacecraft near Jupiter can add one more layer. If a dense patch of ionized gas from the visitor drifts into the outer parts of the magnetosphere, it can excite waves that instruments can hear as a hiss or a whistle. Correlating such a whisper with ground-based images would require coordination and luck. The payoff would be a direct measurement of the plasma content of the tail at a moment in time. Even a failure to correlate tells us the tail is too thin to ring Jupiter's harp at that range. All of this assumes one key step is met first. We must still be tracking cleanly by March. If the post-blackout orbit fit is solid, and if the visitor's brightness remains within reach, the Jovian season can unfold as planned. If fragmentation has reduced the object to a swarm that fades fast, the window will narrow. If the orbit remains uncertain because residuals refuse a simple model, then timing the Jupiter pass will be harder. The community will hedge by booking wide time slots, by alerting networks of smaller telescopes to fill gaps, and by preparing quick reduction pipelines that can turn a night's work into same-night guidance for the next site. There is a narrative tug here that we must resist even as we enjoy it. Jupiter feels like a boss level, the last gate before the credits. In truth, it is one more environment that exposes different physics. If the pass lights up with plasma antics, that will thrill the modelers and push the anomaly score in no direction at all. It will still be nature, loud and beautiful. If the pass shows nothing except a tidy tail and a fading coma, that will also be useful, because it tells us the visitor behaves like rough snow under an electric wind. Either way, the gauntlet is worth running. A one-sentence reorientation, we are testing nature against intention by watching how light, chemistry, and now plasma shape the traveler's behavior as it sweeps past the system's magnetic powerhouse. There is a tempting answer to ambiguity. Go there, not with a telescope from afar, but with a machine that sweeps past the visitor and looks from a few thousand kilometers instead of a few astronomical units. The idea on the table is simple to say and hard to do. Retarget an active spacecraft at Jupiter for a fast flyby of the interstellar traveler. Juno already carries instruments that taste infrared heat, hear plasma waves, and map ultraviolet glow. With the right set of burns at the right times, Juno could in principle arc away from its Jovian loops and meet the object in March. The prize would be close images and spectra that settle debates in minutes. The cost would be risk to a mission that is still delivering science where it is. Begin with the draw. A close pass would see the nucleus, rather than only the coma. It would resolve shape, texture, and any facets that ground-based telescopes blur into a single point. It would measure temperature gradients across the sunward face instead of inferring them from scattered light. It would map gas around the object with enough spatial detail to watch jets form and fade as the body rotates. Plasma instruments would listen to how the coma stirs the charged environment. If there were a smooth facet that sometimes throws a specular reflection, a spacecraft could see it cleanly. If there were fragments arranged in a tidy line, a spacecraft could count them. Questions that demand patience at a distance would find quick answers at speed. Now, lay out the hurdles. Juno was built to study Jupiter. Its trajectory is an intricate dance that keeps it alive in a harsh radiation sea while delivering repeated close looks at the planet. Retargeting would require a significant change in velocity, delivered by a main engine that has rested for years. Propellant budgets would be tight, health margins would be narrow. The flyby would be fast, at tens of kilometers per second relative speed, which means that the window for sharp imaging would be measured in minutes. Pointing and exposure plans would need to be near perfect to come home with more than a streak. There is also stewardship. A working flagship mission sits at Jupiter, still sending results that deepen our picture of the giant and its moons. A retargeting attempt that fails could end that stream. A retargeting attempt that succeeds would still end it soon after, because a fast escape toward the inner system would leave Jupiter behind. Agencies weigh such choices against scientific return, cost, and risk to unique hardware. That accounting is not cold, it is responsible. The interstellar visitor is a once-in-a-generation target. So, is a long-lived orbiter in a world that few craft have ever studied up close for so long. One possibility is a partial compromise. Juno could contribute at a distance without a full intercept. Unretargeted, it could still image the tail from within the Jovian system, and sample plasma changes if the coma clips the edge of the magnetosphere. A competing view suggests that such distant work would add little beyond what Earth can do with large telescopes, and that only a close pass would justify any change in plan. It remains uncertain whether the technical and programmatic gates for a retarget will open in time. Mission teams are careful around engines that have slept. They are careful around budgets that are already spoken for. If a true intercept were approved, the payoff would flow directly into the 5-signal framework. Astrometry would no longer be the only arbiter of tiny pushes. Close imaging would show jets and vents that explain any non-gravitational drift. Spectroscopy from a few thousand kilometers would separate carbon dioxide, water, and other species in space, rather than only in wavelength. Metal lines could be tied to physical sources on the surface, or to particular dust populations. The light curve heartbeat could be matched to visual features such as rotating ridges or pits. Polarization maps could be compared to real textures on the nucleus. Many open questions would either collapse into ordinary answers or explode into decisive anomalies. Even with that promise, we should write down the limits. A fast flyby cannot loiter. It will miss slow changes. It will deliver one geometry and one rotation phase, unless timing luck is extraordinary. It will face dust hazards. It will need the whole community to plan ground-based support so that context is ready before and after the pass. The point is not to imagine a magic picture that solves everything. The point is to decide whether a short, risky look is worth the loss of years of planned work at Jupiter. Public participation can ease the weight of that decision. Citizens can help fill the context map with high cadence, light curves and spectra that frame the intercept. They can help test predictions that a flyby would immediately confirm. If the community builds the robust picture from Earth, the marginal gain from a dangerous maneuver may shrink. If Earth-based work leaves gaps that only a close pass can fill, the case for risk grows stronger. No matter how the decision lands, the lesson is the same. When a rare question passes through reach, the impulse to chase it is strong. The responsibility to weigh that impulse against what we might lose is stronger. If we go, we should go with a plan that wrings every bit of meaning from the minutes at speed. If we stay, we should stay with a plan that makes the most of every night from the ground and from the instruments that can look safely. Either way, the test of our readiness is not only whether we can act, it is whether we can choose well. Here is the quiet secret of big discoveries. They are often made by many small eyes that agree. A rare visitor rewards patience more than aperture size. The plan for citizens and small observatories is simple in spirit and careful in practice. Use modest telescopes to watch often. Use the same methods night after night. Share the numbers quickly with notes that others can reproduce. In a story that turns on trends and timing, cadence is king. A dozen clean measurements from backyards and school domes can fill the gaps between expensive bookings on giant mirrors. The sky does not care which tube you use. It cares that you look when others cannot. Start with light. High-cadence photometry is the backbone. Choose a passband and stick with it. Calibrate each session against the same nearby comparison stars. Keep exposure time steady so that noise behaves. Record the timestamps in a way that can be traced to an atomic clock. Stack short runs if seeing dances, but do not oversmooth. The goal is a living trace that shows how brightness rises and falls across minutes and hours. When rotation signatures begin to emerge, fold the data on candidate periods and send both the raw points and the folded curve to a public archive. Another observer will try the same fold from another longitude. If the beat persists across nights and sites, it earns a place in the main analysis. If it vanishes, it returns to the realm of mirage. Next comes color. When conditions allow, alternate between two filters rather than chasing many. A clean color index across time carries physical meaning. If a brightening is redder than the baseline, larger grains may have joined the coma. If it is bluer, new small grains or gas emission may dominate. Color changes that repeat with rotation speak to surface patches. Color changes that drift slowly speak to seasonal heating as the visitor moves away from perihelion. The community can map both if enough pairs of points are taken in the same sequence. Discipline beats variety. Two colors well measured and repeated will outrun a rainbow of single frames. Spectra are possible with small instruments too. Slitless or low-resolution setups can trace the stronger molecular bands if the target is bright enough. The trick is to observe at the same hour each night to beat atmospheric changes and to keep the processing script fixed. A weak band that strengthens across several days is more convincing than a loud band that appears once. Even a non-detection has value if the limits are reported honestly. Limits fence in the models. A fence is a form of knowledge. Astrometry from small telescopes matters after the blackout as well. The object will be near the predicted path, but every extra point sharpens the curve. Use well-known reference catalogues. Send residuals with uncertainties, not only centroids. If your error bars are large, say so. The fitters will weight the points accordingly. An honest wide point is better than a tight point that hides its doubt. Crowds of points from modest gear can still reveal a coherent drift if one exists. Polarimetry is harder for amateurs, yet not impossible for groups that share gear. Simple linear polarizers can give a crude sense of how the light is oriented. If 3 or 4 sites repeat the same pattern at the same phase angle, the result deserves attention. Even a rough map of polarization angle across the coma can tell us whether the bright sunward bow is filled with larger compact grains or with finer dust. If the pattern turns with rotation, jet models can be constrained. If it does not, scattering physics may hold the answer. Sharing makes the work breathe. Upload reduced data with the methods attached. Post the scripts that did the reduction. Note when clouds passed. Note when guiding slipped. Add a short line about the mood of the night, only if it helps another observer avoid your pitfalls. Public dashboards can display the 5 signals with simple markers that update as new contributions arrive. Green for consistent with natural expectations, yellow for ambiguous, red for odd and repeatable. The legend must be conservative. It should take 2 independent confirmations to move a box to red. It should take clear disagreement to move a red back to yellow. The chart is not a scoreboard for hype. It is a compact weather map for truth. 2 habits keep the playbook honest. First, write predictions in public threads before the next run. Say what you expect the light curve to do. Say whether you think waterlines will strengthen at your chosen wavelengths. Say whether you think the forward glow will fade at your phase angle. Second, celebrate clean refutations. If your night fails to find the feature you hope to find, say so. A refuted guess is a gift to the group. It tightens the search. It proves the method is stronger than ego. A 1-sentence reorientation. We are building a distributed instrument made of many small mirrors and many steady hands, all pointed at the same question. Does the traveler behave like rough snow in sunlight, or like something that keeps its own time? There is a cure for small number magic. Collect more numbers. 3 interstellar visitors are not a pattern, they are a teaser. If we want to, I know whether a low inclination arrival that vanishes into solar glare near perihelion and brushes past 2 big planets is surprising or ordinary. We must build a census, not a scrapbook. That work is starting. New surveys are coming online with wider fields, faster cadence, and pipelines that can spot faint movers skimming the ecliptic as easily as steep interlopers from high latitudes. The promise is that in a few years, we will not be arguing from anecdotes. We will be plotting distributions. Imagine a sky machine that images the same swath of stars again and again with clockwork discipline. Faint points shift between frames. Some are asteroids in our backyard. Some are comets from the outer reservoirs. A tiny fraction carry the telltale signatures of interstellar origin, velocities and arcs that do not close. With enough coverage, the machine does not care whether a traveler hugs the plane or dives steeply. It cares only that the motion is real and repeatable. Night by night, the catalogue grows. Inclinations stack into histograms. Excess speeds lay out along a curve. Perihelion distances make their own shape. Soon, a low inclination path like the one we are following will either sink into the bulk or stay on the tail. Selection effects, our favourite excuse and our honest warning, can be measured instead of guessed. Simulations can inject synthetic interstellar tracks into real survey schedules and ask how many would be found at each geometry. If flat arrivals are overrepresented because our systems stare along the plane, the model will show it. If steep arrivals are undercounted because they cross fields less often, the model will show that too. We will stop hand-waving and start correcting. Once corrected, the true sky will be clearer. If flat, retrograde interlopers remain rare after correction, then the oddness of this case will be real, not the result of where we like to look. Cadence matters as much as depth. A fast survey can see brief brightening events that slower programs smear away. That means microbursts from crust failure are caught rather than mistaken for periodic control. Phase coverage matters too. By sampling a range of phase angles for many visitors, we will learn how often forward brightening appears and how strongly. The signature of large compact grains at certain distances may turn out to be common. If so, a sunward lobe will move from uncanny to textbook, and our sense of mystery will narrow to the residuals that remain after known behaviors are subtracted. Chemistry will join the census. Low-resolution spectra on small telescopes can flag carbon dioxide, rich comet, even at modest brightness. If many interstellar visitors share elevated carbon dioxide early in their approach, then our current case is not alone. If most look like the familiar water-dominated class, then the dry ice dominance here becomes more meaningful. Time series chemistry across many objects will also reveal whether nickel without early iron is a regular pre-perihelion phase or a peculiar choice. The point is not to erase wonder. The point is to place each surprise in a field of peers. There is a wider payoff to this counting habit. It changes how we design missions. If the census shows that interstellar visitors with useful geometries for flybys appear once every few years, space agencies can design small interceptor kits that wait in safe parking orbits. When a target is declared, A kit can sprint and sample without sacrificing a flagship. If the census shows that visits at useful brightness are rarer, then we can argue for occasional heroic retargets with a clearer sense of value. Strategy improves when the dice are counted. One possibility is that the census reveals a wild zoo, with flat paths, steep dives, dry ice worlds, hydrogen stealthies, and boring snowballs all sharing the lane. A competing view suggests that once the biases are corrected, most interstellar visitors will look like the comets we know and the wild. Outliers will be one or two in a decade. It remains uncertain which view will win. What is certain is that arguing from 3 cases is a recipe for mood swings. Until the big surveys fill their databases, we keep our 2 thoughts balanced. Coincidence can stack accidentally, and real patterns can hide in noise. The way out is to count. Today's visitor is a story, and stories can bend. Tomorrow's dozen visitors will be statistics, and statistics will hold us straighter. When the catalogue thickens, the next time a path glides flat into a blackout while brushing Mars and Jupiter, we will know whether to shrug or to call the newsroom. We have lived for many parts with a middle score, a bundle of oddities not strong enough to force a verdict. But scripts must plan for forks. What if the first weeks after the blackout refuse to calm? What if the positions resist jet models, the chemistry clings to its strange ratio, the nickel keeps singing without iron, and the light curve starts to carry a stubborn beat? We do not leap to a headline. We build the next tier of tests, the ones that separate persistent anomaly from clever natural mimicry. First, we harden the astrometry. If residuals remain after the usual non-gravitational terms, we expand the model space. Shape models can be imported from light curve inversions to predict how jets would push over a spin cycle. If even those fail to absorb the drift, we look for directionality that is fixed in inertial space, not in a rotating frame. A fixed push is the red flag. It is still not proof. It is a call to deploy radar if possible, to measure size and roughness directly, and to look for specular flashes that repeat at certain geometries. Second, we tighten the chemical story. If carbon dioxide dominates while heat swings wide, we search for phase-locked variations that ignore temperature. A working fluid scenario would prefer stability across environments. A geology scenario would not. We expand species coverage to include carbon monoxide, organosulfur compounds, and fragments that tie to specific carriers for nickel. If iron continues to lag in defiance of rising temperatures, we ask laboratories to stress nickel and iron, bearing analogues under vacuum and ultraviolet input, to see whether any known mix reproduces the lines and their stubborn imbalance. If no natural recipe fits, the file gets thicker. Third, we attack the heartbeat with discipline. If a cadence holds steady against changing phase, we probe for aliases caused by windowing and by longitude distribution of observers. We inject synthetic clocks into the reduction pipeline to test whether the method fabricates stability. We split the data by passband. A mechanical clock that controls emission might look more achromatic than a dust-driven beat. We also test for geometry locking. For example, does the bright phase line up with a fixed sky direction rather than with the sun object observer angle? Any such lock would be notable. Fourth, we look for structure in space, not only in time. High-resolution imaging during moments of excellent seeing can reveal edges and planes. Lucky imaging stacks thousands of short exposures to sharpen detail near the core. If a flat facet exists and rotates, a repeating glint might mark its passage. Polarization maps can show regions where grains align, or where surfaces scatter like mirrors rather than like clouds. A mirror can be small and still be seen if it is smooth enough and timed precisely. We do not promise that the signals will be large. We promise that if they exist within reach, the patient eyes will find them. Fifth, we strengthen the network. Claims that push the score upward must be replicable across groups that do not share code or priors. The community can coordinate a blind analysis challenge. Teams receive labeled datasets that include real and synthetic anomalies. They run their pipelines without knowing which is which. Scores are compared. Methods are traded only. After results are locked. If a claimed cadence or a fixed push survives that crucible, confidence rises. If it fails, we save ourselves months of argument fueled by a ghost. Even in this escalated branch, language stays sober. One possibility is that a suite of natural processes combines into an exotic, yet still geological story. A competing view suggests that we are seeing active control. It remains uncertain which view the next month will support. The goal of the next tier is not to crown a winner. It is to structure the test so that each outcome adds knowledge. If the anomaly score climbs, agencies must decide whether to commit assets. A small interceptor becomes a better bargain. A distant radar experiment becomes a higher priority. If the score falls back toward ordinary, the same plans become rehearsal for the next visitor, which is its own kind of win. The fork does not demand heat from us, it demands cool procedures. If the score moves, we move with it by adding tests that a natural world should pass and an engineered surface might fail, or vice versa. The audience does not need certainty to stay engaged. It needs to watch the rules work under pressure. That is the real show when nature keeps secrets. The theme that has run beneath the images and the ratios is not aliens, it is readiness. Can a curious culture stare at a rare puzzle without lunging to answers or slipping into panic? The visitor is a test of that civic muscle. The test is not graded on drama. It is graded on how we set expectations, on how we keep promises about evidence, on how we welcome correction, and on how we carry wonder without letting it pull us off the road. Begin with the simple assurances that have to be said out loud in stories like this. The orbit does not threaten Earth. Closest approach is distant by any public standard. Agencies that monitor hazards have stated this in plain language. Repeating it is not dull, it is responsible. It frees the audience to focus on the mystery rather than on fear. It also inoculates the conversation against the lazy slide into apocalypse that shadows so many space stories online. We are safe, we are curious, now we can be precise. Precision starts with the 5 signals. We keep showing the same compact dashboard: position, chemistry, metal pair, light curve, polarization and morphology, green, yellow, red. A small legend, a timestamp. That ritual does more than inform, it teaches. Viewers learn what counts and what does not. They see features move from rumor to replicated to resolved. They watch as green boxes accumulate, and the point of the story tilts toward a natural explanation. Or they watch as red boxes appear in more than one column, and the point tilts toward a deeper anomaly. Either way, the scale moves in public. Hype becomes less persuasive because the rules are visible. Correction must be treated as a virtue, not a failure. If a popular frame turns out to be an artifact, we do not bury it. We tag it in place with an update that shows the fix. We keep the original visible and add the corrected version beside it with a short note that says what changed and why. We do the same with our own predictions. If a forecast ratio does not materialize, we say so, and we adjust the model in daylight. Audiences rarely punish honesty, they punish spin. The best way to keep trust is to surfacing our own errors before someone else does. Language can be tuned without losing heat. Instead of saying this proves, we say this suggests. Instead of saying this cannot be natural, we say this does not match our current models, and here is why. Instead of saying mystery solved, we say this closes one branch of the tree and opens another. This is not cowardice, it is accuracy. It also makes the rare declarative moment, when it arrives, hit with the weight it deserves. We should also talk about joy. The sight of a sunward glow, the first clean detection of a faint iron line, the recovery frame, after the blackout. These are beautiful moments whether the outcome is exotic or ordinary. A culture that only prizes the extreme will miss the deep happiness of understanding itself grow. Show the work. Show the small teamwork between amateur and pro. Show the midnight coffee and the ugly first plots. Show the laugh when a bug is caught. These textures keep a mass audience from drifting into cynicism or conspiracy. They make science human without making it soft. Finally, we set a tone for what happens if the answer stays in the middle. Not every case ends in revelation. Some stay anomalous but unresolved for years. That is not failure. It is an honest reflection of how nature sometimes hides. We can accept that and still be proud of the methods we built, the data we took, and the habits we taught. The next visitor will benefit from all of it. Readiness is cumulative. It is built on dozens of almosts as much as on a few thunderclaps. One sentence to center us before the final turn. Our task is not to name the unknown fast. It is to meet it well, so that whatever emerges from behind the sun, we have the right eyes and the right words waiting. The night after the glare lifts feels heavier than other nights. You can hear the quiet in control rooms. You can feel the breath held in living rooms where viewers have followed green and yellow boxes for weeks. The telescope points, the script that was written before the silence begins to run. We are not improvising. We are not chasing a rumor. We are checking promises. Hook the object. Lock the centroid. Send the coordinates. The orbit fitter breathes, then calls out the first number. The residuals lie where they should, or they do not. If they lie where they should, a cheer goes up that sounds more like relief than victory. If they do not, the room goes quiet in a way that means work, not panic. Either way, the first lever moves. Chemistry takes its turn. Quick spectra flash across the screen with the simple lines marked water rises, or it does not. Iron speaks, or it stays shy. The carbon dioxide band is a tower, or it shrinks to a spire. The second and third levers move. A light curve begins to gather from the small domes that owe nobody time on giant mirrors. Points fill a strip, and then another. Someone folds the first hour on a candidate period, and, for the first time, the heartbeat either lands where models said it would, or it insists on a clock of its own. Polarization maps are slower. They arrive a day later, but they carry the weight of grain sizes, and they tell whether the forward glow was a trick of large compact particles or a sustained feature that asks for jets in a stable geometry. By the end of the first week, the 5 signals have written a paragraph. Not a conclusion. A paragraph with verbs that point. That paragraph can read like this. Positions fit gravity with ordinary jet terms. Water increased as expected. Iron joined nickel as the heat rose. The light curve shows rotation and vent modulation that match a simple shape model. Polarization tracks grain evolution after perihelion. The forward glow softened with phase. The anomaly score drops. This is a real stranger from the deep, yet its behavior is a cousin of comets we have known. The story does not dim. It changes genre, from thriller to documentary about how odd worlds can still be natural. We learn. We cheer the method. We let the mystery relax into knowledge with the pleasure that comes from understanding something that looked, for a moment, like it might refuse us. Or the paragraph can read like this. Positions resist fits that include generous jet models, and the residuals point along a steady inertial direction. Water did not surge as predicted despite rising heat, and the carbon dioxide ratio stayed nearly fixed. Iron remains faint while nickel stays strong beyond thresholds that should have turned the duet on. The light curve shows a stable cadence that does not shift with phase as dust should. Polarization patterns refuse the usual phase law. The anomaly score rises. The story stays a thriller. But the next chapters turn from speculation to demand, to targeted tests that can be falsified. We do not declare contact. We build the next scaffold of checks that an engineered surface could fail. We invite the world to inspect the math. Most endings land between those 2 paragraphs. A few green boxes, a few yellows, perhaps one stubborn red that keeps a debate alive for another season. The visitor will move on either way, across a winter sky and into a thinner light, past the reach of easy instruments, and then into a ledger that future surveys will mine for clues. We will keep watching as it skims the edge of Jupiter's realm, not because it will confess, but because plasma makes beautiful calligraphy on a tail. We will keep listening for the quiet emergence of iron, not because it proves anything grand, but because it teaches how surfaces yield under heat. At the end of this chapter, the larger test remains, the one we set at the start. Could we sit with uncertainty without collapsing into dismissal or hysteria? Did we write predictions in daylight and grade them coldly? Did we show our corrections as proudly as our first guesses? Did we keep the audience close without borrowing fear? If we did, then the outcome is already a kind of victory. The cosmos is not required to give us answers on a schedule. It is required only to be itself. Our job is to meet it with patience, with rigor, and with the joy that comes when the first frame after a long dark finally arrives. The visitor came in on a hyperbola that will never close. It brought a path that hugged the plane, a chemistry that sang in dry ice, a metal duet that began as a solo, and a glow that looked like a lamp facing the Sunday. It also brought us time to practice the habit we will need again, the habit of measuring the unknown with rules that hold, and of telling its story with wonder that does not outrun the facts. The sun gave us a curtain and then it lifted. What we do with the scene now is up to us.